Hello, today let us learn comma notations. Okay, so we have uh, in the comma notations, let us learn gradients. First, let us learn what is gradient of a scalar. Gradient of a scalar. Okay, now let us take a scalar phi. This is phi here. So I want gradient of phi. So gradient of phi, as we all know, is nothing but dou phi by dou x1, dou phi by dou x2, and dou phi by dou x3. That is equal to dou phi by dou x I. I, only one free suffix I, because it is denoting three numbers, no. So it is only one free suffix I. So gradient phi is a vector. So only one free suffix I, that is equal to dou phi by dou xi, that is equal to phi comma I. So comma denotes dou phi by dou xi, the partial differentiation with respect to xi. So phi comma I is a vector. Okay. Now let us go to gradient of a vector. So remember, gradient of a scalar is a vector. Vector is nothing but tensor of order 1. Scalar is nothing but tensor of order 0. So when we take gradient of a scalar, right, is becoming a tensor of order 1. Tensor of order 1. So it is like a promotion. Okay, now let us take up gradient of a vector. Suppose u is a vector, that means having three numbers, right? Then the gradient of a vector u, or you can put an arrow, u arrow, or u tilde, the tilde can be down or up also, right, is denoted by gradient of u or del of u. And we can easily prove that this del of u is a second order tensor. Second order tensor. Now how do you prove this is a second order tensor? First let us see the definition. Then we'll prove it's a second order tensor. Okay, now what is del of u? Del of u is nothing but dou by dou ui by dou xj. Dou ui by dou xj. That is equal to ui. Partial differentiation is denoted by comma here, right? Comma there. So that is nothing but u, right? I comma j. So dou ui by dou xj. That is the denotion of gradient of u. Right. Now let us prove this gradient of a vector is a second order tensor. Fine. So okay, let us take the new coordinates. Let us take a transformation. Let us take new coordinates. So consider our LHS ui comma j dash. That is, I'm taking the new coordinates. Okay, that is equal to dou ui dash by dou xj dash. So let me write it here. So we have, let me take the LHS u I comma j dash. I want the new coordinates, that is equal to dou ui dash divided by dou xj dash. So I'm taking in the new coordinates, right? Now the next step, that is equal to, this is equal to dou by dou xj as it is. We'll keep this as it is. Okay. Now ui dash is a vector. So one alpha will come. So we are going to write the transformation rule. So one bracket there. So alpha. So I is there. So alpha I. Now next is dummy suffix. I should take a dummy suffix. So in the notes we have taken, it is P. It's P U P. Close the bracket. Right. Now next step, that is equal to dou by, now let me take, now UP is in the old coordinates, right? Without dash. ui dash is new coordinates. Without dash is old coordinates, right? Okay. So now the next step, dou by dou x n, we are multiplying xn and we are going to divide by xn, right? So numerator as it is, alpha ip up, close the bracket, right? Into, see, we have divided by dou xn, will multiply by dou xn divided by what was here, that is dou xj dash as it is, right? Now the next step, the next step, that is equal to, okay. So now alpha ip is a scalar, so take it outside, fine. Now what is remaining, I'm writing, so dou u p by dou xn, that is completely old coordinates, right, into dou by dou xj dash as it is, right? Now bracket, this xn I'm writing in terms of new coordinates. So alpha, I have here xn, so it will be the second place n. Now in the first place I can write anything, so we can take m and xm dash. So xn was in the old coordinates, I have written in terms of new coordinates. So whenever we write the old coordinate in terms of new coordinates, this n will come in the second place of alpha. Okay, so now the next step, that is equal to, we'll take alphas outside now, that is equal to, we'll take alphas outside, we'll take alphas outside, so we have alpha ip and alpha mn, we'll take them outside now, so that is equal to alpha ip and one u, this whole thing we can write as u p comma n, right? Alpha mn outside, okay. Then we have dou xm dash by dou xg dash, fine. Let us call this as equation 1, right? Let us call that as equation 1. Now coming to xi. Now let us consider xi. Xi is nothing but what? Having three numbers, x1, x2, x3. Now what is dou x1 with respect to dou x1? Or differentiation of x1 with respect to x1 is nothing but 1. There is 1 there. Dou x1 by dou x2 is 0. Dou x1 by dou x3 is 0. Right? Dou x2 by dou x1 is 0. Dou x2 with respect to dou x2 is 1. Dou x2 differentiation with respect to x3 is 0. x3 with respect to x1 differentiation is 0. x3 with respect to x2 differentiation is 0. x3 with respect to x3 differentiation is 1. So we have 1, 0, 0, 0, 1, 0, 0, 0, 1. This is nothing but identity tensor. So delta ij. So dou xi by dou xj is equal to delta ij. Similarly, that is with the old coordinates. If we take the primes, it is the new coordinates. So dou xi dash by dou xj dash is nothing but again delta ij. So what do we do now? That is equal to now. We'll put it here now. That is equal to, we have two alphas, we'll write alphas, alpha IP, alpha MN. Okay, this whole thing is what now? That whole thing is nothing but delta Ij, right? So U, P, comma N, that is nothing but delta Ij. That is nothing but delta Ij. If it is Inj, but here what we have? We have M now here. So it has to be what? M delta Mj. Now that is equal to, now what is our LHS? LHS we have I, Ui, comma J dash. So how many alphas have come? We'll put the alphas. Alpha IP, alpha Mn, okay, UP, comma N, and delta Mj. Right? I'm just rewriting it. Now that is equal to, now this delta Mj, what are the suffixes? Suffixes are M and J. That means what? This delta can act on this alpha Mn. Look at the suffixes. I have M and J. There's nowhere J here. So I have M and there is M here. Right? So this delta Mj can act on this alpha Mn. So alpha IP as it is. This delta Mj acting on alpha Mn. So in the place of M, we get J. So alpha, in the place of M, we're going to get J, N, U, P, comma N. What is our LHS? LHS is Ui, comma J dash, equal to this much. So two alphas are there. So Ij. So I have I here. I have J here. Right? P is dummy. And N is also dummy. So is it not the rule of, the transformation rule of order, tensor of order 2? So therefore, this Ui, comma J, right, is a second order tensor. Second order tensor. Second order tensor. Right? So gradient of a vector is a second order tensor. Okay, now we shall go to the next part. The next part, gradient of a tensor. Now what is gradient of a tensor? Gradient of a tensor is nothing but, let us take a second order tensor. Let A be a second order tensor with components Aij. Right? Then gradient of A is denoted by grad A, or see, del of A, right, is nothing but a third order tensor. Fine. So what is gradient of A? Gradient of A is nothing but, look at the definition. So gradient of A, if A is second order tensor, this is nothing but third order tensor. So how many suffixes should come? 3 live suffixes must come. Del A I J K. How is that defined? That is equal to dou Aij by dou xk. Right? Differentiation with respect to xk, no? So comma k. Comma k. So Aij, comma k. Fine. And we can easily prove that this is a third order tensor. Just like all the previous one. Right? So whenever we apply gradients, it is like a promotion. So gradient of a scalar is nothing but a vector. Gradient of a vector is nothing but a second order tensor. And gradient of a tensor is nothing but a third order tensor. Whenever you apply a gradient, it is a promotion. The order of that tensor is getting increased by 1. Okay, so let us stop here. The next class, let us learn divergence.